All right, thank you. So we have Matthew Brost from Intel talking about GPU SVM. Welcome.
No? How about now? Okay. I've worked at Intel for about 15 years. The first half of my career I worked on custom high-speed networks, mainly focusing on software simulators, hardware validation. Unfortunately, that didn't work out. So about 5 years ago, I moved over to the Linux graphics team. The first 2 years, I worked on the i9-15 driver, mainly focusing on submission. For the last 3.5 years or so, I've worked on the XE driver, which is the new Intel driver. I was one of the first engineers to start working on that. Actually, Faith was the original author for the POC and then abruptly left Intel. I mainly work on memory management and submission. So what is GPU SVM? It provides drivers like a common way to implement shared virtual memory. For those of you that don't know what shared virtual memory is, compared to like the last presentation where we were talking about VM bind, where you explicitly allocate a buffer object and then bind it into the GPU address space, shared virtual memory would be just using like the C allocators, which that's like malloc or mmap. So the layering of this is GPU SVM speaks to the core MM. It provides like an API that's simpler than the core MM API to implement SVM. And then it also, like as needed, it will call back into the driver with V functions. So the core MM functions it's built on top of are HMM, which is Heterogeneous Memory Management. That's a way to mirror like the CPU address space into the GPU address space. You can do that with one set of page tables or two sets of page tables. In the case of like the XE driver, we do that with two sets of page tables. There's a migrate layer that layer, this is like when you malloc like a CPU address, by default that ends up in system memory. The migrate layer provides a way for GPU SVM to move that memory to device memory. Some of the other APIs we use are like the DMA mapping API. When you need to move memory from system memory to device memory, you need to DMA map it. Lastly, like fully allocation. I mean, if anyone has ever worked with the core MM API before, it's pretty difficult to work with, and that's kind of how GPU SVM came about. So what does GPU SVM provide? It provides an interface to allocate ranges and like functions to walk over these things. So an example of this is when you get a GPU fault, all you have is like an address that's faulted in. Allocating a range lets you create like a larger area over your fault. Typically that's going to be like 2 megabytes because that's the size of a GPU page or a larger one. It handles like MMU notifier creation. An MMU notifier is something you register with the core MM to, like anytime the core MM makes a change to the CPU address space, your driver is notified and you get a callback in an MMU notifier. So yeah, GPU SVM will create these for you And one cool thing it does is it allows you to create these things for like arbitrary sized spaces. That's really key when you want to issue a TLB invalidation. You don't want to issue a lot of these things. You want to issue as few as possible. It provides functions to migrate SVM allocations to device memory. So that would be like when you get a GPU fault, you can have some sort of migration policy which your driver can implement and then move that memory from system memory to device memory. It also provides functions to do page collection and mapping of that. So that would be after you've decided to, after you allocate a range in a GPU fault handler, after you decide to move it, it would be a way to attach the pages to the range and map it so your GPU can understand it, and then go ahead and bind it into its GPU page tables. It also provides eviction support, so that's like when you oversubscribe device memory, if what you decide to evict is like a SVM allocation, it gives you just a single function to call, and you can like evict it back to system memory. It also implements a CPU page fault handler. That should be pretty straightforward. If for example, like if you migrate something to device memory and you have a non-coherent bus, when you get a CPU fault, you're going to have to migrate that back. The GPU SVM implements this function for you. There's locking guidelines. Part of MMU notifiers is there's a fairly complex locking scheme to make like all of this work. GPU SVM will take the notifier lock in every place it possibly can and do it correctly without racing, but then it will also provide the guidelines for the driver side implementation of where to take this lock. And it also has extensive examples in the code, like how to build the driver side components for shared virtual memory. So what are the driver side components? I've already touched on this, a GPU page fault handler. The rough flow of that is you get a fault address, you allocate a range, you decide if you want to migrate it to device memory, you subsequently get the backing pages for that, and then finally bind that into your GPU. Another component is an MMU notifier. I've already touched on that. So that, again, is like when the core MM decides to move memory or whatever it wants to do, you get a callback into your driver. Typically, that resolves to a TLB invalidation or idling your GPU so you can stop all usage of that memory. Another component is a garbage collector. So an example of this would be, let's say your MMU notifier says, hey, I unmapped this memory in the core, and you have backing GPU page tables. You can't just unmap your GPU page tables within the MMU notifier. That's because the notifier is in the path of reclaim. And typically to modify GPU page tables, you need like some locks that are not reclaim safe, like DMA reservation locks, for example. Some other components are like the virtual functions. So there's the common code in GPU SVM, but then there's virtual functions that it needs to call in to do like driver specific operations. Examples of that are you can allocate GPU SVM data structures. The way this is designed, everything on the driver side is designed to subclass the base classes in GPU SVM. So if you need, like a larger structure with more driver side data, you can allocate that. This is actually very similar to GPU VM. A lot of this design was based on that code. Like other V functions would be, let's say you need to allocate device memory. There's a V function for that. The driver can allocate device memory, provide the PFNs, the page frame numbers back to GPU SVM, and then it can go and move memory into that allocation. Likewise, if you want to copy to and from your device, that is the driver side operation. So we have V functions for that. Comparisons to existing SVM implementations. So this was the first implementation proposed as a common solution. AMDKFD has an implementation. NVIDIA's open source driver has implementation. I think Nouveau has some code around this too. That kind of how this started was we started working on this feature, and it got pretty heated on the list. AMD had an opinion, NVIDIA had an opinion, and eventually Dave kind of stepped in and suggested that we do this in a common way. So, well, A, it can be reused by future drivers, B, that we'll actually get this correct. One of the big things that's different in this implementation is the locking semantics are designed around how the core MM works. So that means there's not large device or process locks to seal races. Really everything is just a big retry loop. That's how CPU page faults work in the core MM. So our GPU faults roughly work exactly the same way. And there's no shared locking between those two paths. And those two paths can race. So an example of that, it would be you get a GPU page fault, you start moving the memory over to your device, and then immediately the CPU accesses it. The way that's handled is the GPU page fault handler, like I said, is just a big retry loop. At one of the steps in your GPU fault handler, you're going to detect that the CPU has raced with you, and then you're going to just restart your page fault loop. And whether you try to move it back to device memory, or you just let it sit in CPU memory, that can be based on some policy that a driver has. Another thing that in this design, it's not strictly related to GPU SVM because it's more on our driver side binding code, but we support SVM allocations and BO allocations in the same GPU address space. So the way this works is when a UMD driver loads in SVM mode, it will bind the entire address space to mirror the CPU address space. And then subsequently, if you want to bind in buffer object allocations, you would have to do some sort of baseline C allocation, you could do a malloc or mmap that will get you an address, which you can carve out into your GPU address space and then bind the BO to that address space. So this is, I'm not sure if AMD's code works this way, but this is kind of how CUDA works and how level 0 is designed as well. There's a clear separation between the physical and virtual world. So what does that mean? That means when you get a page fault, or a CPU page fault, you get a struct page. That struct page cannot point to a virtual address. It has to only point to physical memory. The reason for that is imagine a case where the device is faulted in an address, and then you call remap on it. Now your virtual address has changed behind your back, so it really just doesn't work to store virtual addresses in physical things like struct page. User pointer can be built on top of GPU SVM. We actually just landed code for this. For user pointer is explicitly binding a malloc address. This is commonly used in compute UMDs prior to SVM. Okay. Like also, this implementation is extensively documented with kernel doc. Again, this is very much like GPU VM, which has great kernel documentation. I kind of follow the same style as that, because this is common code and make it easy for everyone to use going forward. So what are the status and next steps? GPU SVM is integrated with XE and a single device, and SVM is working. We've implemented user pointer. We've re-implemented user pointer on top of GPU SVM. I think that deleted like 800 lines of code or something in our driver, which was nice. We've also implemented prefetch ioctls. So prefetch would be rather than deferring to your GPU fault handler on first touch, you call this ioctl ahead of time, and it moves the data around for you, faults in your GPU page tables, hopefully saves you, or increases performance a little bit. We've also built madvise on top of this. So madvise would be, it's basically like defining your migration policy, and like, when the GPU faults, do you want to move it? Do you have to move it, etc. We have multi-device. That's a work in progress. I think it's going to be posted, honestly, any day now by my colleague Thomas. The plan support is to start with PCI peer-to-peer with multiple devices, and then once we have hardware for it, build in support for like a high-speed fabric, like UA-Link. We have some performance optimizations upcoming. The really exciting one here is large device pages. Right now, when you move, let's say you have a transparent huge page that was allocated on your system side, and you move that to your device, what that code does is it splits it into 512 4K pages. And the CPU overhead for this ends up being huge. We've profiled our fault handler, and it takes about 300 microseconds to take a 2 megabyte CPU page and move it to your GPU pages. That's just in software. Compare that to like the time to do a copy on like a Battlemage Intel part is about 90 microseconds. So, I mean, you can quickly see where that's a huge bottleneck. But NVIDIA has a series out there to support live or large device pages, and we've profiled that to go from like 300 seconds in software time to about 6. So that's when I think this feature will really get interesting, because prior to this, I think that was like, it was an interesting idea, but I think this part of the kernel just performed so slow, it couldn't really practically be used. But now with like the correct ratio of like 6 microseconds to like 90 seconds copy time, like it starts to get pretty useful. What can make it even more useful is to have like a fully parallel GPU fault handler. So that would be, if you have a single GPU address space, be able to service 2 faults in that address space in parallel. We're basically there in XE, and then this can get really useful, because with 2 CPU threads servicing 2 GPU faults in parallel, you can fetch the data to the GPU at the line rate of the bus. Other optimizations are threaded prefetch, so that would just be like using multiple threads to prefetch data to your CPU. I have some links here for some of the things I've discussed, links to patches, links to kernel doc. Yeah, so are there any questions?
Hello? Good. Yeah, Christian from the AMD GPU team here. First of all, we are planning to switch over our KFD to DRM render nodes. And the idea here is to use the GPU SVM as backing as implementation to replace the SVM implementation we did on the KFD render node. So I actually have tons of questions. First of all, how do you handle pressure from both the graphics as the classic BO interface as well as the SVM interface on local memory on VRAM?
Okay, so our SVM backing storage is actually just a TTM buffer object, so it hooks into TTM's like LRU.
Okay.
Yeah, and then like each page reference count the buffer object. So you can only free the buffer object when the like whatever your range size is, that's your granularity in which you can free it.
Yeah. Okay, next question is how did you do things like multi-device UAPI? Like, for example, madvice on different GPUs.
Okay. I mean, if you're interested, that is actually going to go on the list any day now. But the plan right now is to each device memory region export it as a file descriptor, which you then can pass into your madvice to say this is my preferred region or something like that.
Interesting. Okay, yeah. I need to take a closer look on that.
Yeah,
I probably have tons of questions, so we're going to write up in a mail.
Yeah.
Thanks.
Yeah, well, I mean, it's exciting to see you guys using it. I mean, that's like was the idea when I wrote it, and Dave told me to.
All right, so we're already a little bit over time, so maybe if there are any further questions, we can take them offline right after this talk, but I don't want to keep anyone from their lunch break. So thanks again, Matthew.